Here's a review of the practice questions on page 98 and 99 of your notes. We were working on Earth's history, absolute age dating. So I'm assuming by now you've taken these notes by watching the Ed Puzzle video and done the activity about radioactive decay modeling with the blocks. And let's practice some questions before you do the CASEL learning questions. Here are the answers. Maybe you don't really need to go over these because you got them all right. But the absolute age dating practice questions, we did not do questions 1 through 4. 5A, 6D, 7D, 8, carbon 14, 9C, Nashville, Tennessee, 11-3, 12 was 28,500 years. Go ahead and fast forward. I'm going to go over each question one at a time, but please feel free to go ahead and fast forward through 2 questions that maybe you need some help with that you got wrong. Let's take a look at question number 5. So here's question number 5. What is the approximate half-life of radioactive material X? So radioactive material X is this stuff right here. So I'm going to trace that line. Radioactive material X right there. And they want to know what the half-life is. If you remember from the video, I told you how to calculate right from the lab activity about radioactive decay. It shows you how to get the half-life of something. So if you've got a graph, there's a graph of radioactive decay. You just take half of what you started with. In this case, I started with 80 radioactive atoms. Half of that is 40. So I'll go from 40 over to the line and then down. My half-life, or the amount of time it took to get half the material, amount of time it took, how much time did it take to get to half? Well, I started with 80, half is 40. How long did it take to get to half? It took that long, 2.5 minutes. That was for this. Let's take a look at the graph of the ambiguous. So here is radioactive material X. What's that half-life? Well, we're starting with 100. Half of that would be 50. How long did it take to get to 50? I have to draw my line from 50 over to the line and then down. It took 5. Well, 5 what? 5 times 10 to the third years. Remember, times 10 to the third is another way to say 1,000. So 5,000 years. Correct answer is A. Let's take a look at question 6. Question 6. The diagram below represents the rate of decay of uranium-238. Shaded areas on the diagram represent the amount of what? So we see that we've got uranium-238. After one half-life, only half of that uranium-238 is left. After another half-life, half of that is left. And this question is saying, all right, well, what's this other material? What is this stuff here? Essentially, it's asking, what does uranium-238 decay into? And we just go to the front page of the reference table. Go ahead and take a look. We see that uranium-238 decays into lead-206, Pb206. And that's stable. It's not decayed anymore. Pb is lead. Correct answer 6 is B. 7. Diagram below represents the skull of a saber-toothed tiger that died 30,000 years ago. All right, 400. The age of the skull can be determined most accurately using what? How can you determine the age of the skull? Notice that the 4 choices are the 4 radioactive isotopes that are given on the front page of the reference table. So those are those same 4. Which one of these would be used for a 30,000 year ago saber-toothed tiger? We go back to the notes. If you haven't written, so one of the things we talked about is that carbon-14 was really special. Of the 4, carbon-14 is special for 2 reasons. Why is carbon-14 special? Well, it has a very short half-life compared to the others, only in the thousands of years as opposed to the billions of years. And carbon-14 is organic material. It's found in organic material. So anytime I have something that's organic and has not that long ago, thousands of years, not billions of years, I'm going to use carbon-14. That's the answer to this question here. If I have a saber-toothed tiger that's once living or organic, and notice the time we're talking about is not in the billions of years, but thousands of years, that lets me know I'm going to use carbon-14. So the correct answer is number 7 is B. Question 8. Question 8 says samples of plant pollen are preserved in sediment deposited by the last glacial ice sheet. Which radioactive isotope is best for determining the age of the samples? We mentioned how carbon-14 is a special isotope. Radioactive isotope is special because it has a short half-life, meaning it's measured in thousands of years as opposed to billions of years, and it's found in organic material, meaning things that were once living. So if we go back to this question is talking specifically about that. Question 8 says a sample of plant pollen. Well, plants are organic. During the last glacial ice sheet, that was billions of years ago, thousands of years ago. Remember we mentioned that the glaciers were here in the Rochester area of New York just about 20,000 years ago. If we go back even before that, maybe when some of this plant pollen was preserved, we're still only talking about thousands of years. So the correct answer to 8 is carbon-14. Question 9. If a specimen of a given radioactive substance is reduced in size, its half-life will do what? That means I got a radioactive material. Let's use what we had in the notes for an example. In the notes, we said we started with 400 grams of carbon-14. After one half-life, it dropped to 200. After another half-life, it dropped to 100. They're saying instead of having 400 grams of carbon-14, we're going to cut that in half. If a specimen of a given radioactive substance is reduced in size, so we cut this. Instead of 400 grams, what if this was just 300 grams? What would the half-life be? Well, it doesn't matter. The half-life is still going to be 5,700 years. Even if you get something like this, we say, all right, there's our sample at 400 grams. What if I had another sample very similar to that? What if I did this? I say, all right, we've got this here. Instead of 400 grams of carbon-14, this is 300 grams of carbon-14. What's going to happen to here? Well, it's the same thing. The carbon-14 is going to cut in half. Instead of being 300, it'll be 150 grams of carbon-14. And this will still be our nitrogen-14 over here. Obviously, this here, that's still got 150 grams of the nitrogen-14 in there. But the key to this is that the half-life doesn't change. Just because instead of using 400 grams, we're using 300 grams, this amount of time, this half-life, is still 5,700 years. That does not change. So just because we cut the amount of material in half doesn't mean we change the half-life. So the half-life is going to remain the same. Question 10. A fossil formed 11,400 years ago. Which percentage of the original amount of carbon-14 remains in the fossil? Right, which percentage of the original amount of carbon-14? So let's go through our steps for this. I've got a fossil formed 11,400 years ago. Let's go through these steps of carbon-14. So I start with this much carbon-14, and we'll use the same setup as we did in our notes. So instead of having 400 grams like we had in notes, this is talking about percentages. So we know we're going to start with 100% of carbon-14. All right. After a half-life goes by, how much of that carbon-14 is remaining? Well, we know half-life is the amount of time it takes for half of the material to decay. So half of this material stays carbon-14. The other half, I've got 50% carbon-14. And then I've got half of that is the decay material. And the decay product of carbon-14 is nitrogen-14, so I've got 50% nitrogen-14. And that was one half-life for carbon-14, which is 5,700 years. Well, this is talking about 11,400 years, the question. Now, I'm only 5,700, so let's do another half-life goes by. How much of the carbon-14 is going to be left? Well, it's half of how much is there, so like 50% there, and you take half of that, half of 50% is 25% of carbon-14, and the remainder is going to be the nitrogen-14. So this is 75% nitrogen-14, and the carbon-14 there will be 25%. And that time would be 5,700 years. So from here, from start to where we are right there, is going to be a grand total of 5,700 years plus 5,700 years. And if you do that quick little math, 5,700 years plus 5,700 years, we're going to get 11,400 years, which is what the question is asking about. So now that we've drawn this, it's going to always answer the question. A fossil formed 11,400 years ago. All right, I got 11,400 years. Which percentage of the original amount of carbon-14 remains? How much remains? 25% is what remains. So 10, C. 11. A whalebone that originally contained 200 grams of radioactive carbon-14 now contains 25 grams of carbon-14. How many carbon-14 half-lives have passed since this whale was alive? So same as before, we can create a diagram that'll help us with this. It doesn't matter whether you're using circles or squares, but in this case, I'm just going to write some numbers down. So I'm going to write down. I've got some carbon-14. So I've got some carbon-14 there. It originally contained 200 grams. So carbon-14, I've got 200 grams of carbon-14. After one half-life goes by, remember, half-life of carbon-14 is 5,700 years. If they change this question, instead of talking about carbon-14, they're talking about rubidium-87. We have to change this time. This half-life is just carbon-14. But after one half-life, instead of having 14 grams of carbon-14, I'm going to have half that, or 100 grams of carbon-14. After another half-life goes by, another 5,700 years. I can go again. Instead of having 100 grams of carbon-14, now I'm going to have 50 grams of carbon-14. After another half-life goes by, another 5,700 years. Now I'm going to have 25 grams of carbon-14. I can just continue this process all the way down again and again. But I'm going to stop right now because that's what the question was asking us about. The question said a whalebone that originally contained 200 grams of radioactive carbon-14 now contains 25 grams. All right, that's where we are with the diagram. We went from 200 grams to 100 to 50 to 25. The question asks how many half-lives. Let's count how many half-lives this was. There's 1, 2, 3. So 3 half-lives to get down to 25. Not 4, not 1, 2, 3, 4. 3 half-lives. 1 half-life, 2 half-lives, 3 half-lives to get down to that. That's why the correct answer is 3 half-lives. Question 12. How old is a fossil that is radioactively decayed through 5 half-lives of carbon-14? So let's draw that. Let's draw 5 half-lives of carbon-14. Something going through 5 half-lives of carbon-14. And again, we could draw this like this, like we did there. We could draw this with some circles. We could draw it with some squares. However you'd like to set this up. I'm going to go through 5 half-lives of carbon-14. We have an example of that here in our notes. Here's our carbon-14. 1 half-life, 2, 3, 4. Oh, we just got 4 half-lives. So we would add, let's add another one to our notes here. So there's carbon-14, 1 half-life, 2nd half-life, 3rd half-life, 4th half-life. We want to add one more half-life here. So let's put a line into our notes. We're going to go through one more half-life. Here's the 5th half-life. Instead of having 25 grams of carbon-14, it's going to be 12.5 grams of carbon-14. Just a little bit right there. 12.5 grams of carbon-14. And all the rest is going to be this nitrogen-14. Okay, a little mistake up here. That should be an N for nitrogen. This is all the nitrogen-14. The question that we were asked right here, how old is that fossil that's gone through 5 half-lives? Well, we know that one half-life is 5,700. We know that the next half-life is 5,700. The 3rd half-life is 5,700. The 4th half-life is 5,700. This 5th half-life is 5,700 years. So we're just talking about 5,700 5 different times. All you got to do is do 5,700 years times 5. 5 times 0 is 0, 5 times 0 is 0, 5 times 7 is 30. 5 times 5, 25, 26, 27, 28. 28,500 years. Correct answer. This is 28,500 years.